Extraction of metals. The Earth's crust contains metals and metal compounds such as gold, copper, iron oxide and aluminium oxide. Useful metals are often chemically combined with other substances forming ores. A metal ore is a rock that contains enough of the metal to make it worthwhile extracting. They have to be extracted from their ores through processes such as electrolysis, using a blast furnace or by reacting with more reactive material. In many cases the ore is an oxide of the metal, therefore the extraction of these metals is a reduction process since oxygen is being removed. Common examples of oxide ores are iron and aluminium ores, which are called hematite and bauxite respectively. Unreactive metals do not have to be extracted chemically as they are often found as the uncombined element. This occurs as they do not easily react with other substances due to their chemical stability. They are known as native metals and examples include gold and platinum, which can both be mined directly from the Earth's crust. The position of the metal on the reactivity series influences the method of extraction. Those metals placed higher up on the series, above carbon, have to be extracted using electrolysis. Metals lower down on the series can be extracted by heating with carbon. The extraction method depends on the position of a metal in the reactivity series. Extraction of iron from hematite. Iron is extracted in a large container called a blast furnace from its ore, hematite. Modern blast furnaces produce approximately 10,000 tons of iron per day. The process is demonstrated and explained below. Diagram showing the carbon extraction of iron. The raw materials: iron ore, hematite, coke, an impure form of carbon, and limestone are added into the top of the blast furnace. Hot air is blown into the bottom. Zone 1. Coke burns in the hot air forming carbon dioxide. The reaction is exothermic, so it gives off heat, heating the furnace. Carbon plus oxygen, right pointing arrow, carbon dioxide. Zone 2. At the high temperatures in the furnace, more coke reacts with carbon dioxide forming carbon monoxide. Carbon dioxide has been reduced to carbon monoxide. Carbon plus carbon dioxide, right pointing arrow, carbon monoxide. Zone 3. Carbon monoxide reduces the iron oxide in the iron ore to form iron. This will melt and collect at the bottom of the furnace, where it is tapped off. Iron oxide plus carbon monoxide, right pointing arrow, iron plus carbon dioxide. Limestone calcium carbonate is added to the furnace to remove impurities in the ore. The calcium carbonate in the limestone thermally decomposes to form calcium oxide. Calcium carbonate, right pointing arrow, calcium oxide plus carbon dioxide. The calcium oxide formed reacts with the silicon dioxide, which is an impurity in the iron ore, to form calcium silicate. This melts and collects as a molten slag floating on top of the molten iron, which is tapped off separately. Calcium oxide plus silicon dioxide, right pointing arrow, calcium silicate. Exam tip. For core students, the symbol equations are not needed for the different reactions involved in the extraction of iron from hematite. Equations for extraction of iron from hematite. Extended. The symbol equations for the different stages of the extraction of iron from hematite are: Zone 1. The burning of carbon coke to provide heat and produce carbon dioxide. Cs plus O2 G, right pointing arrow, CO2 G. Zone 2. The reduction of carbon dioxide to carbon monoxide. CO2 G plus Cs, right pointing arrow, 2 CO G. Zone 3. The reduction of iron oxide by carbon monoxide. Fe2O3S plus 3COG, right pointing arrow, 2 Fe I plus 3CO2G. The thermal decomposition of calcium carbonate limestone to produce calcium oxide. CaCO3S, right pointing arrow, SaO S plus CO2G. The formation of slag. SaO S plus CO2S, right pointing arrow, CaCO3L. Extraction of aluminium from bauxite. Aluminium is a reactive metal, above carbon in the reactivity series. Its main ore is bauxite, which contains aluminium oxide. Aluminium is higher in the reactivity series than carbon, so it cannot be extracted by reduction using carbon. Instead, aluminium is extracted by electrolysis. Diagram showing the extraction of aluminium by electrolysis. Exam tip. If you are a core student, you do not need to explain the process of extraction of aluminium by electrolysis. The process of aluminium extraction by electrolysis. Extended. Bauxite is first purified to produce aluminium oxide, Al2O3. Aluminium oxide is then dissolved in molten cryolite. This is because aluminium oxide has a melting point of over 2000 degrees Celsius, which would use a lot of energy and be very expensive. The resulting mixture has a lower melting point without interfering with the reaction. The mixture is placed in an electrolysis cell, made from steel, lined with graphite. The graphite lining acts as the negative electrode, with several large graphite blocks as the positive electrodes. At the cathode, negative electrode, aluminium ions gain electrons reduction. Molten aluminium forms at the bottom of the cell. The molten aluminium is siphoned off from time to time and fresh aluminium oxide is added to the cell. Al3++ 3e right pointing arrow Al. At the anode, positive electrode. Oxide ions lose electrons, oxidation. Oxygen is produced at the anode. 2O2 right pointing arrow O2 plus 4e. The overall equation for the reaction is 2Al2O3 right pointing arrow 4Al plus 3O2. The carbon in the graphite anodes reacts with the oxygen produced to produce CO2. Cs plus O2 G right pointing arrow CO2 G. As a result, the anode wears away and has to be replaced regularly. A lot of electricity is required for this process of extraction. This is a major expense. Exam tip: use oil rig to remember whether oxidation or reduction has occurred at the electrodes.